Okay, so now we're looking at some curve sketches. So today's learning intention is to gain the knowledge in how to use the first and second derivative to help us with sketching curves. We'll be successful if we can add on the first and second derivative as another skill to our sketching techniques or strategies. So just as a recap, so when we're asked to curve a function, we want to really find x and y intercepts. We want to find any asymptotes or anywhere the function discontinues. We want to look at limiting behaviors. We want to determine the domain and range, see if it's odd or even function, or if it's neither. And now we really actually want to find any stationary points. And then we want to find if there's any points of inflection. And when in doubt, then you can use the table of values. Okay, so remember for exams that what we're looking at the sketch, we want it to be big enough so that we can read, so at least around about a quarter of a page. Definitely use a ruler. Label your axes and any key features such as stationary points or intercepts, and use some sort of scale for your axes. Let's do some examples. We want to sketch a curve y equals x squared minus 3x minus 4. Well, we know it's a parabola. We can definitely factorize this. So knowing this, we know we have an x-intercept at -1 and 4. We have a y-intercept at -4. Okay, so we already have some kind of idea. We know it's a parabola. We could find the axis of symmetry. Yep. So which is, from memory, that's meant the form is minus b over 2a. So that would be 3 on 2. All right. And then you can have this vertex. All right. So when x equals 3 on 2, we get -25 on 4. Okay. Now that's how we did it in year 11. What we could do, after we've got these points, what we could do is we could differentiate this. So if the question said using calculus, so I could differentiate this and find the stationary point. And we get the same stationary point. Yep. And then plugging that into you'd get the same y value. So if I was to draw it, -1. Okay, so I've got my turning point here, which is 1.5 and negative 25 on 4. Have my y-intercept, and I have my x-intercepts. Okay, and there you go. Okay. Now what about if they get a bit more confusing, like sketch the curve y equals 2x cubed minus 9x squared minus 24x plus 3. Okay, so I'm going to differentiate it first. Which I can then factor out the 6. Okay, and I can differentiate this again. Okay, and now what I'm going to do is actually going to do, I know, so we want to find my stationary points. So 4 and negative 1. Okay. I'm going to need to know what y equals at these points. So I'm going to, by plugging them back into here, all right, I get, when it's negative 1, I get 43, and when it's 4, I get negative 82. Okay. I want to actually figure out what the concavity is. So by plugging in negative 1 back into here, I get negative 12, so I get a negative number. So being negative 30. So because it's less than 0, that's a maximum turning point. And if I plug in 4, I get a positive number. So I get a minimum turning point. So if I was to sketch that, so negative 1, 1, 2, 3, 4. Okay, so negative 1, okay, y equals 43. And when x equals 4, we get 30, we get negative 82. we get a y-intercept of 30. So the curve would look like that. Okay. All right, so let's do the last example. We've got monosketch y equals 3 cos 2x in the domain of 0 to 2x. So the first derivative is 2 times 3 is 6. Cos becomes negative sine x. Okay, and the second derivative is negative 12. Sine stays the same. Okay, so to find stationary points, while we're here, what I will do is using our old techniques on transformation of functions, of trigonometric functions. Okay. We know that the normal cos function looks like this. And we know that what's happened is we've increased the amplitude to 3, and the normal period of 2 pi happens twice. So that the pattern will happen twice. So even without using trigonometry, we know that the curve 3y equals 3 cos of 2x looks like this. Okay, but let's use calculus. Okay, so we want to find the stationary points. And they occur when the first derivative is equal to 0. Okay, so we get negative 6 sine of 2x equals 0. So sine of 2x equals 0. And now in the domain of 0x to 4 pi. Okay, so sine x equals 0 at 0, pi, 2 pi, 3 pi, and 4 pi. So x would be 0, pi on 2, pi, 3 pi on 2, and 2 pi. Okay, now we want to determine its nature. So determine its nature by plugging in x into the second derivative. So what I might do is I might do a little table. Okay. Now we could find what the x value is. So if you plugged in this, so 3 cos of 0 is 3, cos of, so pi, so it's 3 cos on 2 lots of 90, which is 180, so negative 3. It should just alternate from 3 to 3, yep. Okay, and that's just by knowing our phase has shifted. Okay, and then plugging in these values into your second derivative, all right, so this would be negative 12 cos 2 times 0 is 0. Cos of 0 is negative 1, so it's a negative. Yeah. So because it's less than 0, so second derivative is less than 0, becomes a maximum turning point. Pi on 2, plugging it back into here, just becomes pi. So that's going to be a positive value. This is going to be 2 pi, which is negative value. So which you can, it's going to be positive and that's going to be negative. Just double check. So negative 12 cos of 2 times 360 is a negative number. Okay, so here are all your maximums, and they correspond to here, and then these, as your derivative is greater, is positive than 0, it's a minimum turning point, and they correlate to these points here. Okay, thank you very much. Good luck with it.